Hi guys, thanks for tuning in. In this video, I'm going to talk about thinking in higher dimensions, going beyond three-dimensional space. And the best way to do this is to start with a simpler example. Pretend you had a two-dimensional friend who has never visited the third dimension. How do you, as a three-dimensional being, explain three-dimensional space to your two-dimensional friend? Unfortunately, you're not going to get a lot of mileage out of saying to your friend, oh yeah, like three-dimensional space is just like two-dimensional space, but just add one more spatial dimension. That's not really going to help your two-dimensional friend. Just like if I told you that four-dimensional space is just like three-dimensional space, but with an extra spatial dimension, that's not really going to help, right? You can't picture that. So what are we going to do? Well, we're going to use the mathematics that we learned throughout this chapter, and we're going to say, wait a minute, when I was working with the gradient vector lived in two-dimensional space, but it told me something about a surface that was living in three-dimensional space. Similarly, a contour plot, that exists in two-dimensional space, but it gives us information about a surface that lives in three-dimensional space. So if I can get my two-dimensional friends to understand some calculus, contour plots and gradient vectors, they'll understand quite a bit about how this surface behaves in three-dimensional space, even though they're never going to be able to picture it in their head, and even though they're never going to be able to walk on it, I can help them understand it. And probably the best way to do this is, instead of turning the third dimension into another spatial dimension, for your two-dimensional friend, you should turn that dimension into something else. In physics, you would probably turn it into time, but I think the more intuitive one is to turn it into temperature. So you tell your two-dimensional friend, hey, why don't you go swimming on this contour plot? And the places where the water gets hotter, you're swimming towards a local maximum. And the places where the water gets colder, you're swimming towards a local minimum. And we know some cool stuff, like if you swim perpendicular to one of these level curves, the temperature is going to go up as steeply as possible. And then once we've helped out our two-dimensional friends, we can use that to help ourselves understand four-dimensional space. So look at this. I have an f of xyz equals this equation right here. Now, this is a four-dimensional hypersurface that we can't picture because four spatial dimensions is not really something we can wrap our minds around. But we can plot level surfaces of this four-dimensional surface. Now, if we pretend that f represents temperature, we could basically say, okay, let's plot various level surfaces that represent different temperatures on this surface, on this hypersurface. So here's a level surface that I came up with. I just picked some constant temperature to set equal to this equation, this f of xyz, and that plots out as a surface. Now, we're now kind of like that two-dimensional being. We're the three-dimensional being that doesn't really understand four-dimensional space very well. But now if we're swimming in three-dimensional space, if we swim anywhere on this level surface, we know the temperature in that water is going to stay the same. And we know that if we follow any of these gradient vectors, that they're going to point in the direction of greatest initial temperature increase. So if we swim away from this surface perpendicularly, in the direction of one of these gradient vectors, that's going to be the direction of greatest initial temperature increase on my four-dimensional hypersurface. So I'm not able to picture the four-dimensional surface, but I am able to get a grasp on how it behaves through its level surfaces and its 3D gradient vectors. So just like we could help a two-dimensional being understand three dimensions, we can help ourselves as three-dimensional beings understand four dimensions. Here's another example. I tried to make the temperature thing a little bit more explicit by even just naming the function T of xyz, the temperature in the water at some particular xyz that we're able to pick. And that's how anytime you see an f of xyz, that's what I want you to imagine in your head. Think of f of xyz as the temperature of the water at some XYZ point that you're able to pick, and you're kind of scuba diving and swimming around in the water. And when you evaluate this function at various different points in three-dimensional space, you get a temperature at that point. And, the gradient vector points in the direction of greatest initial temperature increase. If you swim along a level surface, the temperature is going to stay the same. And that's a way of taking our calculus knowledge and applying it to higher dimensions, because we can get some handle on how this four-dimensional hypersurface behaves by putting it into that three-dimensional context that we can more easily understand. Now, I bring this up because this table here should help you get a handle on the different kinds of problems that you might see in your triads. You really want to distinguish between z equals f of xy and f of xyz when you're working through your triad problems. The z equals f of xy example, that's the more standard one to understand. We have a surface living in three-dimensional space. Our level curves live in two-dimensional space. Our gradient vectors are two-dimensional. And so we're using two-dimensional data to understand a surface that lives in three-dimensional space. However, it won't take very long before you start seeing f of xyz's in your homework. And the issue here is this is a four-dimensional hypersurface. We can't really graph this thing. But that doesn't matter because we could still plot level surfaces and 3D gradient vectors for this f of xyz. And if we understand how these gradient vectors behave and how these level surfaces behave, we get some idea of how this four-dimensional hypersurface behaves. And then the other thing is we can kind of take advantage of a relationship here that we know is going to happen, because just like gradient vectors are perpendicular to the level curves passing through their tail, well, 3D gradient vectors are going to be perpendicular to the level surface passing through their tail. So we can actually use an f of xyz to try to find normal vectors. Basically, if you have a surface, if you frame it as a level surface, and then say, okay, I'm going to plot some 3D gradient vectors to this level surface, you're going to get some normal vectors, right? And you're going to see that pop up in some of your triad problems. All right, guys, thanks for tuning in. I hope this was an interesting video. Who would have ever thought that your math career would take you to a point where you're thinking about plotting in four-dimensional space?